Alright guys, so this is part 2 of the videos for Unit 3 review. I'm going ahead and put some notes up here. So remember, we're going to be dealing with growth and decay functions. So remember that growth function, or excuse me, first thing I'm going to look at is the exponent. So if I have a positive exponent like I do here in x, this form a times b to the x again, because this number, this b, could be a times e to the x as well. Okay, and a times e to the negative x. Okay, so that works out as well. Okay, so if that b value is greater than 1, I have growth. If the exponent is positive, if the b value is less than 1, then I have a decay function. This is all assuming that I don't have any type of reflections. And remember, our basic form of the equation, and when I'm dealing with exponents, at least right now, all I'm dealing with are with the a value and the d value. These two down here, which is going to correspond to vertical movement. Okay, so if I have a negative in the exponent, guys, I do have a reflection across the y, though. Okay, so let's go ahead and break down this problem here. First, let's tell if it's growth or decay. So again, right now, just telling if it's growth or decay. So right now, I don't care about these two values, just the 2 to the power of x. So that is a positive exponent. So it's this one's right here where my pin's pointing. And the b is greater than 1, so this is a growth function. Okay, so first thing I want to do is, since this is my a value, this is d, I want to determine the y-intercept. So here, all I'm going to do is plug in a 0 for y. So this becomes y equals 2 times 2 to the 0 power minus 1, which is, again, this is 2 to the 0 power is equal to 1. 2 times 1 minus 1, which is 2 minus 1 equals 1. Okay, so in this particular case, just the numbers worked out that the y-intercept didn't change from the original function. So y-intercept is right here. Excuse me. B, the boundedness, this is bounded below. All of these examples that I had given you are bounded below. But I did move it based on this d value. And since it is a minus 1, I moved it down 1. So originally it's at y equals 0. So if I move it 1 down, now it's at y equals negative 1. So my asymptote is down here. And since this is a growth function, guys, this is moving up, like so. It kind of looks like this. And this should be closer to this line, but something like that. So the end behavior, guys, now I'm talking about the limits as I approach negative infinity and as I approach positive infinity. So looking at this here, over here is the negative infinity number. So you can see that I'm going to end up getting very, very close to the asymptote. And since I'm looking at the y value here is at negative 1. Okay. Over here I have the positive x values. So if I keep going up and up and up, the y value ends up going up to infinity. Okay. So when I have my increasing and decreasing, so since this is a growth function, this is always increasing from negative infinity to infinity. And I have no spots where it is decreasing. Okay, so I want you to write this in a different way. So this right here, guys, is the same as saying y is equal to e to the negative x power. So I want you to go ahead and try and do this one on your own. Again, I will put this in the very last video, the answer for this one, and for this one I'll go ahead and explain a little bit of it as well at that point. So try it on your own and then check yourself at the end of this video. Okay, so now we're kind of doing the same thing, but now with a log function. So leave that there. We're going to kind of need these notes right now, so excuse me. So first thing I'm asking for here is describe the transformation. So I wanted to write here at least what the original graph looks like. So remember, with log functions, I have an asymptote, but now I have it at x equals 0, and I have an x-intercept at x equals 1. So right here. So this is the reference point, so I'm going to start to move around. So if I'm going to describe the transformation, so part A, remember our transformation equation, the one we're using to follow along, is this one right here. So here I can see I have no a value. There's nothing in the front of the log. Here there's nothing in front of the x, so the b value is also not there. I have a c value minus 1 and d value minus 4. Okay, so if I'm looking at this, guys, a c value right here means I move, since it's negative, I move to the right by 1 unit, and a d value right here means I move down by 4 in this case. So this is my transformation right there. Okay, so what that means is essentially I move the asymptote 1 to the right, so it's now located right here. And this reference point I'm also moving, so if it was here at 1, 0, I moved it now 1 to the right and 1, 2, 3, 4 down. So my graph now looks like this red one. Again, you don't have to draw the original, I just did it here for the example. And then part B is asking for the range and domain. So domain is now the smallest x value I can be is 1, so from 1 to infinity, and the range is negative infinity to positive infinity. Again, I use this right here. Okay. Next few problems, guys, they shouldn't take too long to get through. So we did inverses yesterday, and you guys did pretty good on them. So here, first thing I want to do is switch the x's. So x is equal to 6 to the power of y. Now I can here go ahead and turn this into a log function. Remember, if I start with an exponential in the end, I should have a log function. So log base 6, and then I picked up an x equals y. And the y is by itself, so this is the inverse. Okay. Next are the monetary problems, and so this is going to be the last problem I do for this video here. So Jessica invests $1,679 in a savings account with a fixed annual rate of 5% compounded quarterly. What will the account balance be after 10 years? So here, guys, remember, you have to pay attention. You're going to use one of two equations. Here I'm compounding quarterly, right? So that is telling me I have to use this equation. Okay, remember, the other equation I could be using is the PERT equation, which this I will use when I compound continuously. So make sure you're paying attention to your words here. So since it says quarterly, I'm using this. Oops, I forgot the P up in the front. So P value is 1,679. 1 plus my rate, which is 0.05. Quarterly, so this would be a 4 to the 4 times time, which is 10 years. And when I put that in the calculator, I end up having a value of 2,759 and 64 cents. Okay, so try these other two problems, guys. I'll go ahead and go through them again in the last video, just so you all can see what that entails. Especially this last one, number 19. It's kind of not tricky, but it's not as straightforward as these other two problems.